Welcome back, and now that we've briefly gone over the notion of perceptron-based neural networks, we will start implementing one with PyTorch. I've already went ahead and opened up a new collab project that I have named Perceptron, installed Torch, and imported it as well. And in this project, we will be importing a dataset directly from sklearn. And sklearn provides us access to many pre-prepared datasets. And we get access to all these datasets by simply importing datasets. Further manipulating and analyzing this dataset will be done with the aid of a numerical Python library known as NumPy. So we import NumPy as the alias np. You should have seen this before. And importing all the submodules and functions from NumPy into our alias np. And finally, plotting our dataset will be done with the familiar matplotlib library. So we import matplotlib.pyplot as plt. All right, now that we've finished importing the relevant libraries, here's the plan of action. We use sklearn to create a linearly separable dataset. Then using Torch, we create a perceptron-based neural network. Using this neural network, using this perceptron, we will train it to learn how to fit our dataset, such that it's able to separate our data into two discrete classes. We do this with an optimization algorithm that you might be familiar with, known as gradient descent. Before diving into any more theory, let's just start by creating our dataset and keep moving forward. We will import it using sklearn. Recall sklearn provides a variety of datasets to pick from. These datasets come in many different shapes and patterns, so we'll define the number of data points. Number of points is equal to 100, and we will be using the datasets.makeBlobs function to import a dataset. This function creates a cluster of data points that are all randomly centered around a chosen central point for the cluster. We can also choose just how many of these clusters we want, and we can choose the central location at which we want to place each specific cluster. Before we can call the datasets.makeBlobs function, we need to create a nested list that specifies the coordinates of the center of our clusters. So let's call the list centers and define central coordinates for our clusters. This will allow us to have two distinct classes, each defined by its respective cluster data set. Let's center our first cluster on the -0.5 and 0.5 coordinate, and our second cluster will be centered on the 0.5 and -0.5. The exact positions of these centers is not too important. However, these specific positions were chosen to create a reasonably small degree of separation between the data classes, so that they can be effectively classified. We will now create our dataset, and we will store our data points into the variable x, while storing our label values into the variable y, and we'll make use of our labels in just a bit, but essentially, every data point will have its corresponding label. That way, we can train a model to effectively classify the data into different classes. So we then call dataset.makeBlobs and feed into it the appropriate arguments to create our dataset. The first argument represents the number of sample points. In our case, the number of samples is just going to equal the number of points that we declared. Our second argument, random state, we're going to set it equal to just some random integer 1, 2, and 3. And by doing so, this allows us to seed our number generator. That way we can get the same random data sets each time you run your program. That way if there's an error in your model, we can reproduce the error every time. And if you want consistent results as myself, make sure to use the same seed. If not, use any seed you want, it's up to you. And the third argument, centers. This essentially asks for data referring to the center point of each of our clusters. This is where we refer back to the nested list we created above, called centers. the list contains a total of two two-dimensional coordinates that indicate the center point of the data clusters that we want to create. For this reason, it was important to generate those coordinates prior to generating our data set. Alright, we now move on to our final argument that will allow us to generate our very first linearly separable data set. The first argument, cluster std, refers to the standard deviation of the clustered points around their respective centers. A value of 0 would cause all the points to be generated precisely at the chosen center coordinate of the cluster. As this value increases, the generated data points deviate further and further away from their chosen center point. Therefore, we're going to choose a reasonable value of 0.4. This value will allow us to balance between clusters that are too dense and easily separable versus clusters that are too widespread and overlapped. We can now visualize this data, so let's go ahead and print x and y. Before doing so, print x and print y. All right. Notice how x is a 2D NumPy array of x and y coordinates, and the labels are simply zeros and ones, representing our two classes. The datasets are arranged in such a way that the datasets centered at -0.5 and 5, all of them have a label of 0, and the datasets centered at 0.5 and -5, all of them will have a label of 1. This will make more sense to you later on. But finally, after customizing our dataset as desired, we can plot and visualize it using the familiar plt.scatter function. We can define the x and y coordinates of each labeled dataset. Let's begin with the dataset that's labeled 0, the dataset that's centered around -0.5 and 5. We must first access our dataset x, and we'll do a Boolean check. Grab me all the x coordinates that correspond to labels of 0. That is, where the corresponding label in the array y is equal to 0. And clearly all the x coordinates are in the first index of our array, the index 0. All right. Now we also plot the y coordinates of each point, which correspond to labels of 0. Once again, we access the dataset x, and we'll do a Boolean check. Y is equal to 0. Essentially, we'll grab all the y coordinates of the points corresponding to a label of 0. However, in this case, the y coordinate of these data points will be in the second index of the array, namely 1. All right, by plotting this, it plots the top region of our dataset. Now we need to plot all the points in the lower region of our data, which we know correspond to labels of 1. So we repeat this process for the dataset labeled as 1 and copy what we had previously. Instead, now setting the label value as 1 for both the x and the y coordinate. All right, thus grabbing all the points with labels of 1 on the bottom, running the code, we've now created a scatter plot of our data. Keep in mind that x and y are both NumPy arrays. To eventually train a neural model, they must be in the form of tensors. So what we do is back on top, let's just remove the print statement, it's getting annoying. Back on top, what we do is we set x data is equal to torch dot tensor x, and y data is equal to torch dot tensor y. All right, we will be making use of these variables in the near future. For now, feel free to ignore them. And classifying this data will require the use of a perceptron-based neural network. Let's take a break and talk more about that in the next video.